So now we're on to on to section 9.12, and we're going to be talking here about changing distribution of mass. The key idea here, what are we talking about? The application, it's rockets. Okay, so think of like recoil problems, right? If you're holding on to something heavy and you throw it, you get pushed back. But if you're think of like a fire extinguisher on rollerblades, right? There you have a constant stream of particles that are being let out, and then you go in the other direction. That's what happens when you hold a balloon, you blow up a balloon and you let it go, and it flies through the air. Why is it doing that? Conservation of momentum. A lot of mass, it's a constant stream of mass going out. Why does the balloon go all over the place? Because as the little end of the balloon is flapping around, it changes the direction of the force as some of those particles are leaving the balloon. Okay, and so rockets are systems of varying distribution of mass. The mass is changing. Okay, and since the mass is changing, we're not using VIFTAD. The acceleration will probably not be constant, not because the force is necessarily changing on the particles on each other, but because the mass is changing, and so the acceleration will be changing. And so we have this equation, relative velocity. The velocity of the rocket with respect to the Earth is equal to the velocity of the rocket with respect to the products. Products is the stuff that's coming out of the rocket, plus the velocity of the products with respect to the Earth. All right, so let's take a look at some of these equations. These are going to be some just sort of very specific equations that we use just for rockets, and it's the only place we apply them. We've got a few different things here, so we've got to be really careful about our letters that we use in our equations so you know what's what. Capital M is the mass of the rocket, and that is changing over time. Okay, V is the speed of the rocket relative to the reference frame, like Earth. dV is the change in the velocity of the rocket, because it is accelerating. dm is the change in the mass of the rocket. VREL is the velocity of the rocket with respect to the exhaust products. Okay, and then also, by the same token, the velocity of the exhaust products with respect to the rocket. U is the velocity of the exhaust products with respect to the reference frame, which is Earth. R is the rate at which fuel is consumed, and R is negative dm dt, right? Because it's losing mass over time. So here is a derivation. You can look through it if you want. It's based on conservation of momentum, but what we have is this changing mass distribution. And what we end up with at the bottom is this equation T. T is the thrust, by the way. 3 is R VREL equals MA. All right, actually capital M A. All right, that is our first rocket equation. Our next one leads to the second rocket equation. Again, going through the derivation, you can see that we're having to use calculus with, in this case, the changing mass and the changing velocity. And in the end, we end up with delta V is VREL. Remember, that's the relative velocity between the exhaust products and the rocket itself. Natural log of the initial mass of the rocket over the final mass of the rocket. Okay. And then the thrust or the recoil force, that's this. So actually the first and third equations are the same. Okay. And so, to summarize, here's your first rocket equation. And this, we can look at this and think of it as dm dt times vrel, right? Equals ma. Well, this is also equal to m times a is dv dt. And if you follow this through and you add up like over a period of time, so you know your initial and final mass, then you can actually get back to this equation, which is what is done in the derivation. So let's move on to the examples and take a look. The engines of a first one, engines of a spacecraft provide a total thrust of 10 meganewtons. If the exhaust speed is 2.5 kilometers per second, at what rate is fuel being consumed? All right. So let's write out our quantities. Right. A lot of these problems are going to feel like plug and chug. So here we've got T, V rel, and we are looking for the rate at which fuel is being consumed. So what equation are we going to use? And we're going to use this one. Right. So R, solving this equation right here, T equals R. R is T over V rel. So this is going to be 1 times 10 to the 6th over 2.5 times 10 to the 3rd. We end up with 4 times 10 squared kilograms per second. Let's do a unit check on this, make sure it works. Thrust is newtons, so it's kilograms meters per second squared. And then V rel is meters per second. So this is kilograms meters per second squared, seconds per meter. So these cancel out, and we're left with just kilograms per second. So the equation works in terms of the units, and that's a good thing. Okay, so the first question asks for the thrust, right? So T equals the equation we had before, R times V rel. So here's R, and V rel is 1800 meters per second. So this is going to be 3.6 times 10 to the 3rd newtons. Simple enough. B asks for the acceleration at the beginning of the burn. So T equals ma, right? Thrust is a force. And we know the mass. This is only true at the beginning because the mass is what it is at the beginning and then it's changing after that. So that means the acceleration is changing. So the instantaneous acceleration at first is going to be the thrust over the initial mass. And that is 3.6 times 10 to the 3rd newtons over, what do we have, 800 kilograms. So that comes out to about 4.5 meters per second. Next thing is the mass remaining after the burn. Okay. We know the rate. If we do the rate times the time, that'll tell us the change in mass, how much mass has been lost. So this is going to be 2 kilograms per second times 60 seconds. All right, it's burned for, so we lose 120 kilograms. So we start off with 800, we lose 120, and so we end up with 680 kilograms. And then part D, we want to know the change in velocity. So now we're using this natural log equation. So delta V equals V rel natural log mi over mf. V rel we said was, different problem over here, 1800 meters per second. And then the initial mass is what we had before, 800 kilograms. And then we're ending with 680 kilograms. Calculate that, you get about 293 meters per second. Okay. So for 3, here are our quantities. And just think about these for a minute. 200 kilograms per second, that's a lot of mass to be losing every second. Like I have a mass of probably about 80 kilograms, so 2.5 of me every second. And then the stuff is coming out, the exhaust is coming out at 2,000 meters per second, so pretty fast. One way to get yourself going in another direction, to like a big recoil, is either to have a large mass moving in one direction slowly, or have a lot of mass moving over a period of time, but moving very fast. Right? The faster that exhaust, the bigger the recoil is going to be. Right? So if we're looking for the thrust, again, like I said, this is a lot of plug and chug. That's what it feels like. R times V rel. So this is 200 kilograms per second. 2 times 10 to the third meters per second. We end up with 4 times 10 to the fifth newtons. Okay, and then what we're looking for is the change in the rocket's velocity when all the fuel is spent. All the fuel means 80% of this. And so 80%, or rather 20% of this is 4,000 kilograms. That's what's left after the other 16,000 has been spent. All right, so this is my final mass. And so delta V is V rel natural log mi over mf. V rel, 2 times 10 to the third meters per second. Natural log of the initial mass, which is 20,000, over the final mass, which is just the 4,000 kilogram payload. Right. You should end up with 3,218 meters per second. 4. In example 4, we're using the methodology of rocket problems, right? This constant stream of particles, exhaust kind of thing, but to another problem. So here we've got 2 long barges, and they're moving in the same direction in still water, one at 2.78 meters per second, the other at twice that speed. Okay, so while the faster barge is passing the slower barge, coal is shoveled from the slower to the faster at a rate of 1,000 kilograms per minute. How much additional force must be applied to the driving engines to the faster barge so that it can maintain its speed? All right, so let's kind of draw this out. You've got this slower barge going at 2.78 meters per second, faster barge going at 5.56 meters per second. And then you've got stuff going from here to here at a rate of 1,000 kilograms per minute, which, if you convert it, is about 16.7 kilograms per second. Right. And so what's happening is, they want to know how much do you have to drive this engine to keep it moving at this velocity, because as you're adding this mass is coming onto this at a speed of 2.78 meters per second. So that's kind of like the V rel, right? This is the rate, this is R, and V rel is 2.78. So how much thrust is this adding to this? How much thrust does this have to then counteract? And so really all we're doing here is T equals R times V rel. Right? How much thrust is being created by this coal that's being shoveled on? So it's 16.7 kilograms per second times 2.78 meters per second, right? Because that's the difference between those two. And you get about 46.426 newtons, right? That's how much thrust there is due to the constant shoveling of the coal. So this is how much thrust you need to counteract that to keep the barge moving at a constant velocity. And that's it for this packet. And now we're going to go back to the beginning of Chapter 9 and talk about center of mass. So, see you there.